Okay, so this topic is on the bracketing method. So this bracketing method is used for finding the roots of the equation. Okay, so especially uh, we will use this method to find the root of non-linear equations. Because for linear equations or for the equations like polynomial equations up to the power 2, we can find the solution by direct formulas. But for other types of polynomial equations and non-linear polynomial equations, non-linear equations, we need to use the hit and trial to find the solution or to approximate the solution. So we will be talking about the numerical methods. So there are uh, different types of uh, methods. So one of the basic type of such methods is the bracketing method. Okay, these are the methods that exploit the fact that a function typically changes sign in the vicinity of a root. So this is a fact that when we uh, evaluate a function near its root. So for the values of the independent variables less than the root or greater than the root, the signs of the function will be different. So the sign can change from positive to negative or negative to positive, depending on how the uh, function is increasing or decreasing, etc. Also, uh, you can see that these techniques are called the bracketing methods because two initial guesses for the root are required. So the name of this method, as it suggested, that the which is bracketing method, is due to this reason that we bracket the solution. That means we try to enclose the solution in the form of a bracket, in the form of a narrow space. Okay, and we make with the further iterations, we make this space narrow and narrow. Okay, and then that's why the name of this method is the bracketing methods. For it is not just one method; these are more than one method. So that's why we are using the term bracketing methods with S over here, not method, not just method. So, namely, we will specifically, we will be talking about three kinds of methods: graphical methods, bisection method, and the false position method. Uh, so, graphical, bisection, and false position method. In fact, you may not know that, but you may already be using these methods for solving sometimes the uh, non-linear equations. Okay, so normally we call such a method as the hit and trial method, okay, or trial and error method, trial and error method. But in a more in a more sophisticated way, we adopt certain methodology, and depending on our methodology, we can call either of you can call these methods either of these names, either the bisection method or the false position method. The graphical methods are more generic then the bisection, and the false position method. So we will first look at the graphical methods to understand the concept, the whole concept, and then we will look at the bisection and the false position methods. Okay. Uh, do you have any question regarding this introduction?
No.
Okay, so graphical methods. So in the graphical methods, what you do is, it is a simple method for obtaining an estimate of the root of the equation. The equation we will represent in the form of f of x, that is the a function in terms of x, and then we will equate it to 0. And then this will be the standard form of the equation. So to make a plot of the function and observe where it crosses the x-axis. So because if we plot this function on x and y axis, okay, so wherever the plot will cross the x-axis, that position of x will be the root of the equation. So this point, which represents the x value for which f of x is equal to 0, provides a rough approximation of the root. Of course, that point which is at which the uh, function crosses the x-axis is that point is the root of the equation. However, in the graphical method, we can just estimate it because graphical method will not give you the exact value, because that estimation will depend on how accurately we can measure or we can scale it from the graph. Okay, so the answers may vary from one person to another person within the level of the precisions. Okay, so that's why this method provides a rough approximation of the root. Okay, let's see it with the help of the example. Use a graphical approach to determine the drag coefficient C needed for a parachutist of mass m is equal to 68.1 kilogram to have a velocity of 40 meter per second after free falling for time t is equal to 10 second. So note the acceleration due to gravity is 9.81 meter per second. So for example, if there is a parachutist, okay, so that is a parachutist falling down, okay, and then when that parachutist is falling down, that parachutist is uh, that parachutist is falling down, okay, and then as the parachute is falling down, it is accelerating, but due to the friction from the air, there will be the opposite forces, okay, and these opposite forces will help to decelerate that parachutist down, and in the end the parachutist will fall down at a constant velocity, okay, but what will be that drag coefficient? So if the constant velocity is reached something like 40 meter per second, okay, so then what will be that drag coefficients? So although this problem has been given to us, we don't need to analytically solve this equation, so we can just use the uh, uh, we can just use the uh, equation which has already been derived in the first chapter of this equation, or from your engineering understanding, you can derive these equation for the solution. So the equation for the solution is this. F of C is equal to Gm over C into 1 over e power minus C over m into t minus v. So basically, you will derive the equation in terms of the velocity and then rearrange the term to write the formula for in terms of this C. Okay, so therefore, in this solution, if we can, if we want to find the value of C for this function is equal to 0, then that will be the solution. Okay, so this problem can be solved by determining the root of this equation using the parameter t is equal to 10, that is 10 seconds. That means after falling for 10 seconds, the velocity has to be 40 meters per second. But then what should be the value of the drag coefficient? Value of the drag coefficient. So, so for that equilibrium case, the value of this drag coefficient should be found out from this equation. But here in this case, you can see that we cannot determine C, for which f of C is equal to 0 directly. So we have to do the trial and error method, or even if maybe you can try to determine by the direct method, but here we are doing it with the help of the numerical method as well. Okay, so we have this, let me erase it. Yes. Okay, so now I have this, now I can input the values into this equation. The g is the acceleration due to gravity, m is the mass 68.1, c we want to know, and 1 minus e we already know that it is the value of the it is a constant. C we want to know, and then mass is 68.1, and t is the time, and minus v, that is for it is the velocity. So now we have this function in terms of C. Okay, in terms of C. So in the graphical method, we can plot this function. In the graphical method, we can, sorry, what's happening? So in the graphical method, we can plot this function, okay? And let's simplify it. So we have 99.81 times 68.1 is 668.06. And we get like this. So because C over 68.1 times 10, so 10 over 68.1, it is minus 0.16, minus 0.146843 C minus 40. So then we can try in this equation, various values of C can be substituted into the right hand side of this equation to compute the value of the function of C. So if, for example, if you take your calculator and then the values of various values of C. So for example, if you put the value of C is equal to 10, so 668.06 divided by 10, and then you will calculate the value of f of C. So you can use this the same equation and then input different values of C. So value of C is 4, then f of C is 34, value of C is 8, f of C is 17. So as we are increasing the value of C, the value of f of C is decreasing, and until we can see that at some point the value of C changes from plus to minus. So uh, roughly at an interval of 4, 8, at an interval of 4, the values have been plotted. So it means that over here, because for the for this function, the value of this function changing from plus to minus between for values of C between 12 and 16, then the root will be between 12 and 16. So here you can graphically plot it. And from this graph, now you can see that the value will be approximately, if you plot it on some graph paper or on Excel, then you can directly read the solution. So therefore, in this case, that the solution is between 12 and 16. So the visual inspection of the plot provides a rough estimate of the root, which is about 14.75. Of course, then you have to read it very carefully. So if it read it very carefully, so if it is 12 and this is 16, so it is somewhere between 12 and 14, and then you have to visually estimate it whether it is 14.5 or 14 itself or a little bit more than 14. So uh, so you have to zero in on and to at this point and then measure it uh, in a rather precise manner. So the validity of the graphical estimate can be checked by substituting it into the original equation. Okay, so if, for example, if you substitute this value of 14.75 over here, and then what will be the value of f of c? So it should be closer to 0. So for example, now if we put this value 14.75 back into this equation, so it is now 0.1, so which is relatively which is close to 0. So it means that here this graphical method is providing us a reasonable solution. So which is close to 0. It can be checked by substituting it into the other equation along with the parameters values from this example to give velocity. So for example, if we want to calculate the velocity, so the velocity, the formula for the velocity will be v is equal to gm over c into 1 minus e power minus c over mt. And the velocity should be equal to 40 meter per second as we have used before. But in this case, the velocity we have calculated is about 40.1 meter per second. So which is not 40, but also not very much different from 40. So it means that we have got a reasonably well solution with this graphical method. So this was the example 5.1. There are graphical method, although useful, but it has a limited practical value because this method is not precise. By not precise, I mean that different people can use this graphical method and they may come up with different results within the precision levels. Okay, so for example, if one person for example, in the previous case, one person may measure the value of the solution to be 14. The other person may measure the value of the solution to be 14.25. Another person may measure the value of the solution to be 14.6. So although the solution may not be very much different from the each other, but there will be some level of imprecision in the different measurements in this method. So this method is not precise, so therefore it has a limited practical value. Uh, this method can be utilized to obtain rough estimates of roots. So, however, this method is useful only for obtaining the rough estimates of the roots. More precise estimates of the roots are not possible or very difficult to achieve by this type of method. So now let's look at different types of cases in the graphical methods. So here in this case, you can see that we have plotted a function of x, and in this case, we can see that while this function of x is plotted, you can see that this function is increasing from negative value of a negative value, that means it is below x, to positive value. So it is increasing from it is an increasing function from negative to positive value at a point from some lower point to an upper point. So the lower and upper points are represented by these blue dots, and the intersection with the x-axis has been represented by the uh, uh, black dot. So here in this case, you can see that this function has only is exhibiting only one solution between the lower and upper limits of the estimates. Okay, so in the as we can see that in the bracketing methods, we have to have some estimates, and those estimates are taken in which that means those lower and upper estimates of the solution are taken within which the original solution should lie. Okay, so in this case there is one solution, but later on we will also generalize this rule for other cases. So in this case, the single root is bracketed by the negative and positive values of f of x. And here in another case, you can see another function. Okay, the function can be any type. So here in this case, in this function, you can see that there are three roots. Okay, so in this case, the function is changing value from positive to negative. Okay, but here you can see that the function is changing the root, changing the value from positive to negative, but it has three roots over here in this case. So from here, we can, from these two graphs, we can make a general idea that for many of the functions, when the value of the function changes from negative to positive or positive to negative, we may have odd number of roots. Okay, so here we have the 1, here we have the 3 roots. Okay, so we may have the odd number of roots. So however, this solution, this type of conclusion is not, there are some exceptions to this rule as well. Okay, so this is not an absolute rule which is applicable to every situation, and there are some exceptions to these rules as well, and those exceptions we will come across later on. Okay, but for many general cases, it is like that. So if there is a change of sign, okay, if there is a change of sign of the function from negative to plus, or from plus to negative and minus, there are then usually odd number of roots, 1, 3, 5, 7, etc. Okay. Okay, so now look at the second observation. The second observation is that here in this case, you have a function which does not become 0 for any value of x. Okay, so we take any two values of x, and both values of x gives you the positive value of the function, and then we can see that that function never touches down on x. So it means that in this case there will be no solution. There will be no solution. And having no solution, it means it is zero, and zero is an even number. Okay, so we can make a conclusion that if the value of a function between two values of the independent variable are of the same size, either positive or either negative, then we may have no solution or an even number of solutions. So for an even number of solution, we may have this kind of situation. So for example, here we will see that both extreme lower and upper bound values are positive, but in between this function is touching down on x at two values, first at here, another at here. So this will mean that this function will have two solutions. So it means that if the function has the same uh, sign for two given values of x, then that function will have an even number of solutions. So even means either 0 or 2 or 4, like that. It cannot have the odd number, because if it will have odd number, then that the third point will be under this x-axis, and then the next point will have to be a negative. But here uh, the upper and lower limits are both positive. Okay. However, there are still exceptions to this rule as well. So rather the odd number of roots or the even number of roots, there are some exceptions. Okay. So one of you has said that can't it to be the tangent of x? Yes, it can be to the tangent of x, and that I am going to show as an exception in the next slide. So talking about the graphical methods, here you can see that you can have this kind of situation as well. So here you can see that at this dotted point is touching down on this x-axis at just one point, and then it is not going into the zero range. So it is touches down, it becomes zero, and then rises again. So below, before this point or after this point, the value is both positive. So in this case, this point is at the tangent to this axis. So therefore, there is an exception to this rule. So here you can see that now we have only two roots. Okay, two roots of this function between these two limiting values. So lower limit and the upper limit. Lower limit is the value is positive. The upper limit, the value of the function is negative. So according to the first rule, there should be odd number of roots. That means 1, 3, or 5. However, in this case, there are even number of roots. So one is here, the other is here. So therefore, that first rule simply does not apply to this situation. However, one may argue that this type of root mathematic can be called as the double root. So this therefore, essentially this rule can be considered as 2. So then 2 plus 1, that will be 3. So in that case, that rule will apply. But of course, there are different types of arguments. You can give both of the arguments are true. So therefore, there are exceptions, or if you look at another way, so there may not be, that rule will still apply. So these are called as the multiple roots that occur when the function is tangential to the x-axis. So for this case, although the endpoints are of the opposite sign, there are an even number of axis intersections for the interval. As a second case, as a second exception, you may have this kind of function. So there are some functions which are discontinuous at some point. So for example, this function, when changes like this, so as the value of x increases, Okay, so this function goes up and crosses the x-axis and then go into the negative side. Okay, and but right after that, another branch of the function starts from the positive side and then go towards that side. So from the lower and the upper bound, here you can see that although both uh, uh, points are starting from the negative to the positive values of the function of x, but there are even number of roots in this case because the function was discontinuous. So therefore, in order to apply that odd or even number of roots, we have to follow certain restrictions. That means the function should not be a discontinuous function. So for the discontinuous function, or for that function in which there are some multiple roots, these rules will not apply. So therefore, we need some special strategies for determining the roots of these cases. So those special strategies or methods we will consider in the later topics. So let's look at example 5.2. The use of computer graphics to locate the roots. So since we are just talking about the graphical method, so let's complete it with before finishing this lecture today, and then we will start on time the next lecture. And the computer graphics can expedite and improve your efforts to locate the roots of the equation. So for example, if we say, take this function sine 10 of x, sine 10x plus cosine 3x, and if we plot this from 0 to 5, then we can determine, we can see that this function, which is a nonlinear function, will have several roots. So you can plot it with the help of any package such as Excel, MATLAB, etc. And you can see over here is that if you plot it, so the plot will look like this. Okay, so you can see that this plot is crossing the x-axis at several points. Here, 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 here. Okay, here if you want to see that this point seems to be the double root, or this point seems to be tangent to this x-axis. So whether it is really the tangent to this x-axis, or it is just looking as the tangent to this x-axis, that we can see by zooming in into that area. So for zooming in, we can plot the graph at a narrow range. So in this case, previously the plot was graphed from 0 to 5. Now we plot the between the range of 3 and 5. So if we plot between the range of 3 and 5, so we can see that it still looks as a tangent. So can we further zoom it? Yes, we can zoom it. We can further zoom it. We can maybe zoom it from 4 to 4.5. And then if we further zoom it, then we will see that from 4.2 to 4.3, and then we change the y range from minus 1.15 to 0.15. So we can see that this plot is actually not tangent to the x-axis. Okay, so it is not. So it is. It was just looking as the tangent to the x-axis when we have plotted it at a smaller scale. So when we zoomed in, then it is actually found out that this has actually two roots which are quite close to each other. So for example, it may be 4.26 and 4.24 and 4.26, nearly those points. Okay, so therefore, the graphical solution, as it was suggested before, gives you the approximate methods as well, approximate solutions as well. It cannot be very accurate. So for the initial guesses, the graphical method can be useful, or for understanding sometimes for understanding how the values are changing in the function, the graphical methods can give you some very good ideas. But for more accurate or more precise results, graphical methods may not be used because it has some limitations. Okay.